Ever get that feeling where you're just staring at a mountain of information, maybe research papers, spreadsheets that seem to scroll forever, and you just wish there was a way to instantly see the hidden gems?
Yeah, the key insights without getting totally lost in all the noise.
Exactly. Well, that's kind of where we come in.
Think of us as your shortcut to understanding. You send us the complex stuff, the sources you want to grasp.
And we, your expert guides for this deep dive, do the heavy lifting. We extract the essential knowledge nuggets for you.
Right. So you can get the core ideas quickly, thoroughly, and hopefully, get a few of those satisfying aha moments along the way.
And today, for our listener, the learner, we're tackling a really interesting piece of research they shared. It's called UAA, Uniform Manifold Approximation and Projection for Dimension Reduction.
Okay, UAAP. Now, dimension reduction might sound a bit jargony.
It does, yeah.
But it's actually a super useful technique in data science.
Yeah.
Really fundamental.
Imagine taking really complicated information, maybe something with tons of different variables or features, and kind of squeezing it down.
Right, distilling it into just a few key ingredients.
So you can actually see what's going on, maybe
Yeah.
in a visual chart or just to get it ready for, other machine learning algorithms.
Absolutely. I mean, in today's world, we're just swimming in data, aren't we?
Totally.
And the ability to simplify these complex data sets is, well, it's more important than ever. It lets us spot patterns that would otherwise be completely invisible.
Uh-huh.
And it makes it much easier for machine learning tools to work effectively, especially with really large amounts of information.
Right.
So understanding how these tools work is like a real superpower for anyone dealing with data.
Okay, so let's unpack this source a bit more for the learner. This paper introduces UMFP. It's presented as a novel way to do something called manifold learning.
We'll definitely get into what manifold learning means in a moment.
Yeah, and it's built on some pretty serious mathematical ideas. Things about, like, shapes and connections and data drawn from geometry and topology.
Right. The authors, Leland McInnes, John Healy, and James Melville, they make some pretty bold claims right at the start, don't they?
They do. They say UMP is competitive with the kind of current top dog for visualization, which is called TSNE.
Often pronounced T-SNE.
Right, TSNE. But they say UMP is faster. It does a better job of keeping the sort of global structure of the data intact.
Which is a common critique of TSNE, actually.
Ah, okay. And they also say UMP isn't limited in terms of the embedding dimension, how much you simplify it.
Meaning it's useful for more than just making those 2D or 3D pictures. It can be used for actual machine learning pre-processing.
Exactly. So potentially a much more versatile tool.
And what's fascinating, and the authors really emphasize this, is that UMP isn't just some algorithm they, threw together.
Right.
It's built on a strong theoretical foundation using mathematical principles. They argue that for this kind of task, finding patterns without labels, unsupervised learning, having that solid theory, is incredibly important.
Makes sense. Gives you more confidence it's not just finding random noise.
Precisely.
Okay. So our mission today, the learner, is to cut through any potentially complicated math and get straight to what UMP is really all about.
Yeah, why it's significant and how it might be useful for you in practice.
Even if some of the terms sound a bit out there, we'll make sure you walk away with a clear understanding.
So where should we start? Maybe with the basic problem. Why do we need dimension reduction in the first place?
Good question. Well, think about it. We're constantly collecting more and more data.
Right, absolutely. Exploding.
And a lot of it is what we call high dimensional. It has a huge number of different pieces of information, different features for each item we're looking at.
Could be hundreds, thousands, even millions of features.
Exactly. Now, trying to visualize something with, say, 1,000 different characteristics, it's impossible for us humans to wrap our heads around.
Right. Our brains are good at, like, 2 or 3 dimensions. Maybe 4 if we squint.
Dimension reduction helps us squeeze that massive information down into maybe 2 or 3 key aspects so we can actually see if there are groupings or trends or maybe some weird outlier.
Precisely. And beyond just looking at the data visualization, it's also crucial for getting data ready for machine learning.
Ah, right, the pre-processing step.
Yeah. If you have too many features, sometimes called the curse of dimensionality, it can really bog down the algorithms.
It makes them slow.
Slow, yeah, it makes them take forever to run. And sometimes it can even lead to worse results, where having more information actually hurts the algorithm's ability to learn general patterns.
Counterintuitive, but yeah.
So reducing the number of features while keeping the important underlying structure. That can seriously boost the speed and accuracy of machine learning models.
And as the paper points out, it's pretty essential for dealing with the massive scale of data sets we're seeing now.
Definitely.
Now, the paper mentions there are kind of two main families of techniques for doing this.
Broadly speaking, yes.
First, you've got methods that try to keep the distances between all pairs of data points roughly the same, things like PCA, principal component analysis, and some others.
Right. They focus on preserving the overall variance and global distances.
Then you've got newer methods, relatively speaking, that focus more on preserving local distances, making sure that things that are close together in the original complex data stay close together when you simplify it.
And that's where techniques like TSNE, ISOMAP, and large Vs come in.
Yeah.
And UME falls squarely into this second category.
Focusing on those local relationships.
Exactly. Really prioritizing keeping neighbors together in the lower dimensional map.
Okay, so let's get to the core idea of UMEP itself. What actually makes it tick? What's the fundamental approach?
At its heart, UMP tries to do two main things. First, it tries to figure out the hidden structure, the underlying geometry of your high-dimensional data.
Like a shape the data lives on.
Exactly. Imagine your data points aren't just scattered randomly in high-dimensional space, but maybe they lie on some kind of twisty folded surface within that space. That surface is what we call a manifold.
Ah, so that's manifold learning. Learning that hidden shape.
Precisely. Discovering the hidden lower dimensional shape on which your high-dimensional data might actually lie.
Okay, so first find the manifold. Then what?
Then, UMP tries to create a lower dimensional representation, like a 2D map, that preserves the essential structure, especially the connectivity, of that manifold.
So if 2 points are close on the manifold, they should be close on the map.
That's the goal.
You used an analogy earlier, like taking a rumpled blanket, the high-dimensional data, and smoothing it out on a bed, the lower-dimensional space.
Yeah, that's a pretty good way to think about it. You want to smooth it out, but without tearing it or distorting the local patterns too much. You want the parts that were close on the rumpled blanket to still be close on the smooth bed.
Okay. And UMA uses some, you mentioned sophisticated math to do this.
It does. It borrows ideas from Riemannian geometry, which deals with curved spaces and distances on them, and also from algebraic topology, which studies shape and connectivity in a more abstract way.
Wow.
Specifically, the paper mentions it builds on earlier work on something called Laplacian eigenmaps,
Heard of that one.
and also uses concepts related to something called fuzzy simplicial
The
sets.
fuzzy simplicial
Yeah,
sets. Okay. That still sounds a bit intimidating.
it does, admittedly. And even the paper itself acknowledges that the really deep mathematical details might not be for everyone.
Phew.
But the main takeaway, I think, is that UMA uses these advanced mathematical tools to build a representation of how the data points are connected to each other in the high-dimensional space.
Like a network or graph.
It's exactly a sort of fuzzy graph where connections have strength. Then it tries to create a similar graph structure in the lower dimensional space. We don't need to get bogged down in the specific equations.
Good.
But knowing that there's this strong mathematical underpinning gives us confidence that the algorithm isn't just making things up. It's based on solid principles about structure and topology.
Got it. So fancy math helps it understand the data's inherent structure, and then it aims to make a simpler version that mirrors that structure. Okay. Now, the paper really shouts about some key advantages of What are the big selling points they highlight?
Well, there's several significant benefits they point out. First off, and this is a big one, they claim it provides competitive visualization quality compared to TSNE.
So the pictures look as good.
Pretty much, yeah. For a long time, TSNE has been the go-to for creating those insightful 2D and 3D scatter plots that help us see clusters and relationships in complex data. UMA aims to deliver comparable results, often showing the same kinds of groupings and separations.
Okay, so it matches the state of the art for visualization. What else makes it stand out?
Crucially, the authors argue, and provide evidence, that UMP arguably does a better job of preserving the global structure of the data compared to TSNE.
The big picture structure.
Exactly.
Right.
TSNE is fantastic at showing you these tight-knit local clusters, right?
Yeah, it really separates things out.
But sometimes, in doing that, it can kind of distort the larger distances. Things that were far apart originally might end up looking closer than they should, or the relative arrangement of different clusters might get warped.
Ah, I see.
UMP, with its theoretical underpinnings in topology, aims to give a more faithful representation of both the local and the global structure, how the different parts of the data relate to each other overall.
So, using your earlier analogy, TSNE shows the neighborhoods clearly, but UMP gives a better map of how the whole city is laid out.
That's a great way to put it.
Yeah.
And for understanding broader trends or relationships between different groups in your data, that preservation of global structure can be really important. It's a potential game changer.
That makes a lot of sense. You want the details, but also the context. What else?
Another major plus they emphasize is runtime performance and scalability. This is huge.
Faster.
Significantly faster than most TSNE implementations, especially as datasets get larger. We're talking potentially orders of magnitude faster for millions of data points.
Wow, okay. That's not trivial.
Not at all.
Yeah.
And it scales better. It also doesn't have the same computational restrictions on the embedded dimension, the number of dimensions you reduce down to.
Right, you mentioned that.
TSNE is typically used for 2 or 3 dimensions for visualization, and running it for, say, 50 dimensions could become very slow or impractical. UMAP handles higher embedding dimensions much more gracefully.
Which makes it suitable for.
For using the reduced dimensions as input features for downstream machine learning tasks, not just for making pictures, it becomes a more general-purpose dimension reduction tool.
So for the learner, if they're working with those enormous data sets we talked about, UMP isn't just a bit faster.
No, it could potentially move analysis from, let's run this overnight, or for days to let's run this in a few hours, or even minutes. It fundamentally changes what becomes feasible.
Okay, that's a really compelling advantage, a practical workhorse, not just a visualization tool.
Precisely. And the paper also notes its growing real-world adoption, even back when it was written. It was being picked up in fields like bioinformatics, analyzing cell data, material science, and various machine learning applications.
That practical uptake is usually a good sign.
It suggests it's solving real problems for people.
Okay, UMP sounds pretty impressive. Now, maybe we can dig a little deeper into how it actually does this.
Yeah.
The paper breaks it down into 2 main phases, right? Graph construction and then graph layout.
That's right. Those are the 2 core computational steps.
Let's break those down for the learner. What happens in that first step, graph construction?
Okay, so the first phase is all about building that initial representation of your complex, high-dimensional data using connections like a network or graph.
Representing the relationships?
Exactly. It starts, like many similar algorithms, by looking at each data point and finding its k nearest neighbors in the original high-dimensional space. The k closest buddies based on some distance measure.
Ah, k nearest neighbors. That concept pops up a lot. So for each point, it figures out which k other points are most similar.
Correct. And this number k, often called neighbors in the software implementation, is a really key parameter you can tune. We'll come back to that.
Okay.
Then UMP does something clever. For each point, it calculates a sort of local distance scale. It looks the distance to its absolute nearest neighbor, Roy in the paper's notation, and also figures out another scaling factor, sigma, that helps define how far the neighborhood of that point stretches. This helps the algorithm adapt to regions where the data might be very dense or very sparse.
So it adjusts its idea of close depending on the local density.
Exactly. It's locally adaptive. Using these distances and local scales, UMP then determines the strength of the connection or the weight of the edge between a point and its neighbors. It uses a specific mathematical function, an exponential decay, so that closer neighbors get a stronger connection weight.
Closer means stronger link. Makes sense.
And they interpret this weight in terms of that fuzzy simplicial set idea. It's like the probability or the membership strength that this connection exists. Think fuzzy not as unclear, but as representing degrees of connection, not just yes or no.
Okay, so not just connected, not connected, but how connected?
Precisely. Initially, these connections might be directed. The strengths from point A to B might differ from B to A.
Yeah.
So the final part of this phase is to combine these potentially asymmetric relationships into a single undirected graph. It uses a probabilistic logic, specifically a fuzzy set union or T-connorm, where the final weight of an edge between 2 points represents the probability that at least one of the directed connections exists between them.
Ah, so it symmetrizes the relationships in a principled way.
Yeah, ensuring you capture the mutual closeness. The output of this whole phase is a weighted graph where the nodes are your data points, and the edge weights represent the strength of similarity or connection between them in the original high-dimensional space.
Okay, so step 1. Build this fuzzy, weighted map of connections based on local neighborhoods in the original data.
Yeah.
Got it. What happens in step 2, the graph layout?
Step 2 is about taking this abstract graph, this map of connections, and finding a good way to arrange the points, the nodes of the graph, in a low-dimensional space, like a 2D plane for visualization.
Drawing the map, essentially.
Exactly. And UMP uses an optimization technique that's conceptually similar to force-directed graph layout methods. You can imagine forces acting on the points.
Forces, like
It's
physics.
a bit like that, yeah. Imagine that connected points with a high edge weight from step 1, are pulled together by an attractive force, like a spring.
Okay, neighbors attract.
And then there's also a repulsive force acting between all pairs of points, pushing them apart slightly. This prevents everything from just collapsing into a single clump.
Makes sense. Keeps things spread out.
The strength of the attractive force depends on the edge weight calculated in the first phase. Stronger connections pull harder. The repulsive force is generally weaker and act between all points. The exact mathematical forms for these forces are derived from trying to minimize the difference between the graph structure found in step 1 and a similar graph structure defined in the low-dimensional space.
So it's trying to make the low-dimensional arrangement match the high-dimensional connections.
That's the core idea. It's optimizing an objective function called cross-entropy, trying to make the probability distributions of edge existence as similar as possible in both high and low dimensions.
Okay. And how does it actually find that optimal arrangement?
It uses an iterative optimization process, often stochastic gradient descent. It starts with an initial placement of points in the low-dimensional space.
How does it get that initial placement? Randomly.
Sometimes it can be random, but UAP often uses a smarter initialization. It can use something called spectral layout, which looks at the overall structure of the graph, specifically the eigenvectors of the graph Laplacian, to get a pretty good starting configuration.
Ah, using the graph structure itself to start.
Yeah, and this smarter initialization often helps the main optimization converge faster and find a better final layout, making the whole process more efficient and stable.
So it starts with a decent guess based on the graph structure, and then it iteratively adjusts the positions using these attractive and repulsive forces until it finds a low-dimensional arrangement that best reflects the high-dimensional connections.
You've got it. That's the essence of the graph layout phase.
Now, you mentioned some adjustable settings, these parameters.
Yeah.
The paper highlights neighbors and mindest. You said neighbors was key in the first step. Let's revisit that. What does it actually control for the learner?
Right, neighbors. This parameter basically controls the balance between focusing on very local structure versus more global structure when UMP is building that initial graph.
Yeah. How many neighbors it looks at.
Exactly. A smaller value for neighbors, say 5 or 10, tells UMP to focus on the very immediate neighborhood of each point. This can be great for capturing very fine-grained details and separating small, tight clusters.
But the downside?
The downside is that it might miss the bigger picture, how these small clusters relate to each other. And it can be more sensitive to noise in the data. If the data is noisy, a very small neighbors might cause UMP to find spurious structures, patterns that aren't really meaningful.
Like seeing faces in the clouds, as you said.
Precisely. The paper shows an example with noisy data on a color cube, figure 1, where a low neighbors makes the noise look like elaborate structure, while a higher value smooths it out to reveal the true cube shape.
Okay, so what happens if you use a larger neighbor, say 50 or 100?
A larger neighbors forces UMAP to look further afield, considering more points when defining the local structure. This has the effect of smoothing things out, averaging over more neighbors. It becomes less sensitive to noise and better at capturing the broader, more global structure of the data, but you might lose some of the very fine local detail.
So it's a trade-off, local detail versus global overview.
It really is. Choosing the right neighbors often depends on your data and what you're trying to see. It's probably the most important parameter to experiment with.
Okay, that makes sense. What about the other one, mindest? You mentioned it affects the layout phase.
Yes, mindest, which stands for minimum distance. This parameter controls how tightly packed points are allowed to be in the final low-dimensional embedding, the output visualization.
How close together points can get.
Essentially, yes. It influences the repulsive force in the layout optimization. A smaller minus value, closer to 0, allows points to clump together more closely. This might give a more accurate representation of the data's topological structure, showing dense clusters as very compact.
But the potential issue is...
The plot might become very dense and cluttered in those regions, making it hard to distinguish individual points or see structure within the clusters.
Okay, so what if you increase mindest?
A larger minus value forces the points to spread out more. It increases the minimum distance allowed between points in the low-dimensional map. This generally makes the visualization cleaner, less cluttered, and easier to look at, especially in dense areas. It prevents overplotting.
So a low mindest is maybe more truthful to the density, while a high mindest is more for visual clarity.
That's a good way to think about it. The paper suggests that MINDIST is often considered more of an aesthetic parameter, controlling the visual appearance, while neighbors have a more fundamental impact on what structure is captured.
I see. And the paper shows examples of this too.
Yes, figures 2 and 3, using handwritten digits, pen digits in MNIST datasets, do a nice job of illustrating how changing both neighbors and MINDIST affects how the different digit clusters are separated and how much space there is between points within each cluster.
So, the learner, these are the main knobs you get to play with. Neighbors to tune the balance between local and global structure, and MINDIST to control the packing density in the final plot.
Exactly. Experimenting with these is key to getting the most informative results for your specific dataset and questions.
Okay, this is starting to click. We build the graph based on neighbors, lay it out with forces, and tune it with these parameters. Now the crucial part, how well does UMAP actually perform in practice compared to the competition?
Right. The paper dedicates a good chunk to empirical comparisons. They test UMAP against several other dimension reduction algorithms, TSNE, of course, but also variants like FIT-SE, another method called large VS, older techniques like Laplacian eigenmaps, and the classic PCA.
And they tested on various data sets.
A whole bunch. Standard benchmark datasets like QL image datasets, shuttle satellite data, MN East and Fashion MN Digits clothing, even large text data, Google News, and some real-world biological data like flow cytometry and single-cell RNA sequencing data. A pretty comprehensive evaluation.
Okay, and what were the main findings? Did UMAP live up to the hype?
In terms of runtime, the results are pretty striking. UF8 was consistently among the fastest, often significantly outperforming TSNE and large FAs, especially on the larger datasets.
So the speed claims hold up?
They seem to, yes.
Hmm.
They also tested how runtime scaled with the number of data points, the embedding dimension, and the original data dimension. UMAP showed favorable scaling compared to TSNE, particularly when increasing the embedding dimension or dealing with very high dimensional input data.
Good scalability is key nowadays. What about the quality of the results? We talked about visualization. How did it fare more objectively?
Well, visually, as we discussed, the paper argues UMP is competitive with TSNE and large face, producing similar cluster separations, but potentially with better preservation of global structure.
Yeah.
They show several figures comparing the output side by side.
Right, and the objective measures.
They used a quantitative measure, key nearest neighbor classification accuracy. The idea is, if the dimension reduction preserves the local structure well, then a simple classifier trained on the low-dimensional data should still be able to accurately distinguish between different known classes in the data.
Makes sense. If points from the same class stay close together, the classifier should work well.
Exactly. And the results, shown in tables and plots, tables 1 and 2, figures 5 and 6, indicate that UNAP performs very competitively. It generally achieved classification accuracies comparable to, or sometimes slightly better than, TSNE and large phase, especially when considering not just the immediate neighbors, local scale, but also slightly larger neighborhood sizes, non-local scales.
So quantitatively, it backs up the claim of preserving meaningful structure.
It seems to, yes. It performs well on this task, suggesting it's effectively capturing the separability of the classes in the low-dimensional space.
They also mentioned something about stability.
Ah, yes. They looked at how stable the embeddings are if you run the algorithm on different random subsets of the data. Ideally, the overall structure should look similar each time. They used a flow cytometry dataset, figure 8, and found that UMP embeddings appeared qualitatively more stable and consistent across different subsamples compared to TSNE embeddings of the same data.
Which is good. You don't want wildly different results each time you run it.
Exactly. It suggests the structures UMAP finds are more robust.
Okay, so UMP seems like a strong performer overall. Fast, scalable, produces good visualizations, preserves structure well both locally and globally, and seems reasonably stable. But, as we always ask, no algorithm is perfect. What are some of UMP's limitations, or situations where it might not be the best choice for the learner?
That's a crucial question, and the paper is reasonably upfront about some limitations. One key aspect is interpretability.
We touched on this briefly.
Right. Unlike linear methods like PCA, where the resulting dimensions, principal components, often have a clear relationship back to the original input features.
Like this dimension represents overall size or something.
Exactly. With UMP, because it's performing a complex nonlinear transformation based on manifold assumptions, the resulting dimensions in the low-dimensional space don't typically have such a direct, intuitive meaning. They represent abstract directions along the learned manifold.
So if you need to explain why 2 points are close in the UMP plot in terms of their original measurements, It's harder.
Much harder, yes. The axes themselves don't usually correspond directly to specific combinations of original features in a simple way. So if that kind of direct interpretability of the dimensions is critical for your analysis, a linear method like PCA might still be preferred despite its other limitations.
Okay, interpretability is one trade-off. What else?
Another consideration is its behavior with very noisy or very small data sets. UMP fundamentally assumes that your data lies on some underlying manifold structure.
It's looking for that structure.
Right. If the data is mostly random noise, or if you have too few data points to reliably infer a manifold, UAMP might still find some structure. But it could be spurious. It might just be amplifying noise into patterns that look meaningful but aren't actually real.
That faces in the clouds problem again.
Exactly. So you need to be cautious when applying it to very small data sets. The paper suggests potential issues under a few hundred samples, or data you suspect is dominated by noise. Interpreting the results requires care.
Good caveat. Assume structure, might find false structure if none exists. Anything else?
Well, while UMAP aims to capture global structure better than TSNE,
Yeah.
its core mechanism is still heavily based on local neighborhood information.
The K-neighbors.
Right. If your absolute primary goal is to preserve the entire matrix of pairwise distances between all points as accurately as possible, capturing structure at all scales simultaneously, then methods like classical multidimensional scaling, MDS, might theoretically be more appropriate, although they're usually computationally much more expensive and don't scale well.
So UMAP is a balance, focusing on local but doing a decent job globally, whereas MDS tries for everything but costs more.
That's a reasonable summary. Also, there's the point about data density. UMAP's underlying theory involves an assumption that the data is, roughly speaking, uniformly distributed on the manifold.
Uniformly distributed. But real data often has dense clusters and sparse regions.
Exactly. And because this underlying assumption, UMAP tends to spread out points in the low-dimensional embedding to make the density more uniform than it might have been originally. While MINDIS controls the minimum separation, the overall effect is often an evening out of densities.
So it might make very dense clusters look less dense and sparse regions look less sparse.
It can, yes. If preserving the relative densities and the actual distances in the original space is critically important for your specific analysis task, then UMP's transformed view, which prioritizes topological structure over metric distances, might not be the ideal representation for that particular purpose.
Okay, so it really boils down to understanding what aspects of your data structure, local topology, global relationships, metric distances, density variations, interpretability are most important for the question you're trying to answer.
Precisely. No single-dimension reduction method is universally the best for all tasks. UMP offers a particularly powerful and computationally efficient approach focused on topological structure. But you need to be aware of its assumptions and potential trade-offs.
That's really helpful context. So UMP sounds like a fantastic tool, especially for exploring large, complex data sets and for machine learning preprocessing, but it's good to know its specific strengths and where it might have limitations. Looking ahead now, what about the future? Does the paper hint at where UMP might go next?
It does. The authors outline several exciting potential avenues for future work, leveraging the technique's strong theoretical foundation.
Such as?
Well, they mentioned extending UMP for semi-supervised learning, where you have labels for some of your data.
Yeah.
And you want to use that information to help guide the dimension reduction process.
Ah, using the labels to improve the structure finding.
Exactly. Also, adapting it to handle heterogeneous data types more naturally. Data sets that mix numerical features, categorical features, maybe even text or images. That's a common challenge.
Definitely. Real-world data is often messy like that.
Totally. Another interesting direction is developing efficient ways to add new data points to an existing UMAP embedding without having to recompute everything from scratch. That would be incredibly useful for dynamic or streaming data.
Oh, yeah, incrementally updating the map.
And maybe even the flip side, generating high-dimensional data from points in the low-dimensional UMAP embedding. This hints at potential applications in generative modeling.
Going from a simple map back to complex data. Interesting.
Yeah. They also list things like metric learning, learning a better distance measure as part of the process, and importantly, developing techniques to better detect and mitigate those potentially spurious embeddings you might get with small or noisy data sets.
Improving robustness and reliability.
Exactly. And the paper notes that even at the time of writing, experimental versions of some of these extensions, like semi-supervised UAP and handling diverse data types, were already being developed in the reference software implementations.
So it sounds like UAP isn't just a static algorithm released into the wild, but more of a foundation, a framework for ongoing research and development in understanding complex data.
I think that's a perfect way to describe it. Its strong theoretical roots in topology provide a really solid platform for building more sophisticated data analysis tools.
Well, the learner, we have certainly taken a pretty comprehensive deep dive into this UMP paper today.
We definitely covered a lot of ground.
Let's try to quickly recap the main takeaways for you. UAP is a powerful, relatively new technique for dimension reduction simplifying complex data.
It's grounded in some pretty solid mathematical theory about manifolds and topology.
Key advantages: it's fast, it scales well to large data sets, and it produces high-quality visualizations that are competitive with and arguably better at preserving global structure than the previous standard, TSNE.
Right. It's also versatile, useful not just for visualization, but also as a pre-processing step for machine learning, because it handles higher embedding dimensions efficiently.
We learned it works in two main steps. First, building a fuzzy graph representing connections in the high-dimensional data based on local neighbors.
And then finding a low-dimensional layout of that graph using force-directed optimization, aiming to match the topological structure.
And you, the learner, have key parameters to tune, especially neighbors, controlling the local global balance, and MINDIST, controlling the visual density.
But remember the limitations. The reduced dimensions aren't easily interpretable in terms of original features. It can find spurious structure in noisy or very small data sets, and it prioritizes topological structure potentially at the expense of exact metric distances or density variations.
And finally, it's an active area of research with exciting potential for future extensions, like handling semi-supervised tasks, mixed data types, and incremental updates.
That's a great summary. Hopefully you now have a much clearer aha moment about how a technique like UMP provides this really potent way to peer into complex, high-dimensional data.
Yeah, revealing that underlying structure, that hidden shape, in a way we can actually understand or use.
And understanding these kinds of tools, the learner, can really empower you. It helps you gain insights from your own data, navigate research more efficiently, just make sense of the complexity.
We definitely encourage you, if you're interested, to explore the original paper further, or maybe check out the UMP software implementations. They're readily available online.
Yeah, try it out on some data, and maybe start thinking about how dimension reduction, whether it's UMP or something else, might be relevant to the kinds of data or problems you encounter in your own field or interests.
And maybe a final provocative thought to leave you with. Consider how this ability, the ability to translate incredibly complex data sets into simpler, often visualizable forms, can unlock completely new discoveries and understandings. It works across so many diverse fields, from biology to astronomy to social sciences. What hidden patterns, what undiscovered relationships might be waiting right now to be revealed in the data that you encounter every day, if only you had the right lens to see them.
Deep stuff indeed. A powerful question to ponder.
Well, thank you so much, The Learner, for sharing this fascinating paper with us. It was a great source for a deep dive. And thank you for joining us.
Yes, thanks for listening. We hope you found this exploration of UMP insightful and useful. Until our next deep dive.